Happy Wednesday, you guys. Hope you all are doing well. Um, we are about to finish chapter 5. So there's one last section that I want to go over that is about a new collection of functions that we haven't talked about in the past, but may come up in the future, especially if you end up taking a course later on differential equations, and I'll explain a little bit more later. But we're leaving behind so section 5.6 and 5.7 are on differential equations. That's the only part of the book for us that we're actually going to get into differential equations. We're not going to circle back on those anymore. Again, if you take future courses on differential equations, you'll end up investigating that a little bit more. This is just it was just a little bit of a taste of differential equations there. But there's a section really the last section of chapter 4. It's section 5.10, and it's on a special collection of functions called hyperbolic, trigonometric functions, which is a big mouthful. Hyperbolic trigonometric functions. We call these hyperbolic trig functions. You may not have ever seen these before, and that's okay. What I want to do is I want to give you a little bit of motivation for where they come from, and then I'll talk a little bit as I explain what these functions are. We'll explain why they're called hyperbolic functions, why they're called trigonometric functions. They're going to be related to the trig functions that we are much more familiar with. So let me give you a little bit of motivation here. Recall here. One of the things that one of the the banes of the existence of any calculus student is the fact that when I differentiate sine, I get cosine. But when I differentiate cosine, I don't get sine back. What happens? When I differentiate sine, I get cosine, but when I differentiate cosine, what happens? I get negative sine. And that negative is like the thing that everybody hates, right? Because when you integrate, you have to go backwards, and you have to remember that the derivative of cofunctions is negative, and it's just annoying. So one question we could ask is, are there any functions that we know of that when I differentiate one of those functions, like are there two functions f and g where when I differentiate f, I get g, but when I differentiate g, I get back to f again. So not like this. Here, if this was my f and this was my g, differentiating g doesn't get me back to f. But are there two functions out there that when I differentiate f, I get g, and when I differentiate g, I get f again? Can you think of any examples where that actually works? Well, kind of a silly example, but it turns out this actually does work, would be if I started with e to the x, and I differentiate, I get e to the x, and then if I differentiate back, I get e to the x again. Okay, so e to the x is kind of a silly example, but that works. Can you think of, and then a constant times e to the x, that's kind of also a silly example. Can you think of any other examples that would work? This is another example of a pair of functions that would work. If I started with e to the negative x and differentiate, what is the derivative? What derivative do I get there? That turns out to be negative e to the negative x, right? Do you remember that? If we had e to the 2x, the derivative is 2e to the 2x. So if the function is e to the negative x, the derivative is negative e to the negative x. But when I differentiate again, I get another negative that comes out that kills this first negative, and I get back to my original function again. So these two functions have this nice property, whereas sine and cosine end up with this negative after two derivatives. Okay. What about the following functions. And you may wonder, where in the world did I get these functions? I'll explain what the motivation behind this is. But let's start with the function e to the x minus e to the negative x over 2. In other words, 1/2 e to the x minus e to the negative x. Okay? Again, I'm not going to motivate where this function's coming from. Don't worry about that right now. But if I started with this function, what would the derivative be? Okay, we're going to leave the 1/2 alone. What's the derivative of e to the x? E to the x. And then the derivative of negative e to the negative x, that negative is going to come down and I'm going to have a positive e to the negative x. Okay? So that's the first derivative. Let's call that g. Okay. What's the derivative of g? Well, if I take another derivative here, my e to the x stays e to the x, but what happens to this term? I get e to the negative x, and then I get another negative out front. So we end up with f again. So in other words, this function differentiates to this function, and then this function differentiates to this one. Okay? It turns out these two functions right here, this one, or this one, and this one, we're going to give these a special name. Okay, we're going to call the first one hyperbolic sine. So in the terminology that we use here is we use sine with an h at the end. Okay, so hyperbolic sine of x, we're going to call that e to the x minus e to the negative x over 2. In other words, 1/2 e to the x minus e to the negative x. And then we're going to call the other one, my g over here, we're going to call that hyperbolic cosine. Okay, and so we're going to write cosine, C-O-S, with an h of x, and that's going to be e to the x plus e to the negative x over 2. Okay, in other words, 1/2 of e to the x plus e to the negative x. Okay, these are two new functions. Now, I haven't explained why I'm using these, why they're called hyperbolic, why are we calling them sine and cosine. I'll give a little bit more explanation here, but we're going to call this hyperbolic sine, this special function right here, we're going to call this special function hyperbolic cosine. Now, first, let me say, everybody gets tired of saying hyperbolic sine and hyperbolic cosine. So you notice that this is spelled C-O-S-H, so almost everybody says cosh here. So nobody says cos. You can't really say that. So everybody says cosh of x here, so that's hyperbolic cosine. And then up here, you can't say sine or sin. So everybody says here sinh. So this is called sinh of x, and this is cosh of x. But where these come from, they're called hyperbolic sine and hyperbolic cosine. So let's explain a little bit, first of all, why are these called hyperbolic functions? Okay? I'm going to just kind of leave this here for a second. Why are these called hyperbolic functions? Well, the motivation behind it is that, if you remember, there's an equation that says cosine squared of some angle plus sine squared of some angle equals 1, right? That's a trig identity that you're used to. That's with normal trig functions. That's true. All right? Cosine squared plus sine squared is 1. That's something that we know to be true. Okay? And you'll notice that if we substitute cosine, we typically refer to as x, and sine we think of as y. This x squared plus y squared equals 1 is exactly our unit circle. Okay, so this is related to a circle. All right, so trig functions are related to a circle, and all of this is stuff that should not be shocking. Okay. It turns out that if you take cos squared of an angle minus sinh squared of that angle, let's just go ahead and do this, okay? So we're going to take cos this function 1/2 of e to the x plus e to the negative x, and we're going to square that. That's our cos squared, but I'm not using x, I'm using theta, so let's do that. Okay, minus, let's take our sinh, so 1/2, use round brackets here, e to the x minus e to the negative, and I'm not using x's, sorry, using thetas, squared. And let's see what happens. Okay, so we're squaring the 1/2, that becomes a 1/4. And we're squaring e to the theta plus e to the negative theta. So let me just write 2 copies of those so we can multiply those out. Okay, minus, again the half is squared, we've got a 4th, and I'm going to write e to the theta minus e to the negative theta, e to the theta minus e to the negative theta. Now, what I'm about to show you, I'm going to derive a formula here. You don't have to write this down, but the formula that we get to the end at, you will need to write down, okay? So you can just sit back and watch right now. This is not super critical that you have this in your notes other than the formula that we eventually get to, okay? So we've got 1/4. Okay, I've got e to the theta times e to the theta is e to the 2 theta. Remember, that's e to the theta squared. It's 2 copies of e to the theta multiplied together. So it's e to the 2 theta plus e to the theta times e to the negative theta. This is actually like e to the theta times 1 over e to the theta. That's actually 1. So if I'm foiling first, the outer term, this times this is 1. Inner is also 1. And the last term is e to the negative 2 theta. Okay. And that was square brackets. You see that? I just foiled. E to the 2 theta, 1, 1, e to the negative 2 theta. Minus a 4th, and then here we have e to the 2 theta minus 1 minus 1 plus e to the negative 2 theta. Okay, so what we've got here, if I pull the 4th out of everything, we've got an e to the 2 theta plus 2 plus e to the negative 2 theta. Again, I pulled that 4th out over here, so I've got a minus e to the 2 theta. Minus minus is plus 2 here, minus e to the negative 2 theta. So what you'll notice here is if I've got an e to the 2 theta minus an e to the 2 theta, those go away. And these go away, so I'm left with just 2 plus 2 is 4. So I get 1 here. So in other words, cos squared minus sinh squared is 1. So cos squared minus sinh squared is 1. Again, if I think of my cos as an x and my sinh as a y, this formula right here actually relates to, just like x squared plus y squared equals 1 is a circle, x squared minus y squared is actually a parabola. Sorry, not a parabola. What am I saying? It's a hyperbola. Hyperbola. And that is why these functions are called hyperbolic functions. That's where the name comes from. They satisfy an equation that is a hyperbola. So that's why these functions are called hyperbolic functions. And this kind of also answers the question that maybe you were asking, why in the world did I throw this 1/2 on here? The 1/2 is there so that this equation works out correctly, so that I get cos squared minus sin squared equals 1. If I didn't put that half on here, we would actually get cos squared minus sin squared equals 4. And I don't want a 4 there. I want it to match these two equations really nicely. So that's why that 1/2 is on there. Okay? So that's why these are called hyperbolic trig functions. Now, I haven't explained really why they're called trig functions yet. We'll get to that in just a second. You can see a little bit of analogy between this trig function, these trig functions, and these trig functions. We'll get to more in just a second. But let's actually look at what the graphs of these two functions look like, okay? So, the graphs of these two functions, let's start with hyperbolic sine. So sinh of x. This ends up looking like, so if this is e to the x over 2, and if this is negative e to the negative x over 2, then sinh actually ends up looking like this. Okay, it approaches e to the x over 2 up here, and negative e to the negative x over 2 down here. Okay, part of the reason is that if this is 1/2 of e to the x minus e to the minus x, when x gets big, this thing goes to 0. E to a really big negative number is really, really close to 0. So when x gets big, this term goes away and it basically becomes that function. When x gets small, this term goes to 0. And this one becomes really big, and so it basically becomes, if I can delete just that e to the x part, it becomes negative e to the negative x over 2 there. Okay? You'll notice this function right here is odd. Okay, it goes through the origin. It's odd because it's symmetric. If I were to flip it 180 degrees, it would look the same. And the domain is all real numbers, and the range is all real numbers. Okay, notice that about this equation, this graph here. Okay, let's go ahead and graph hyperbolic cosine. So you have the graph of that as well. Okay. So y equals cos x, so that's 1/2 e to the x plus e to the negative x. Now, one thing you'll notice is if you plug in x equals 0, I get 1 plus 1 is 2, divided by 2 is 1. So this goes through the point 0, 1 there. And when x gets big, again, this term goes away, and we're close to e to the x over 2. Okay, and when x gets small, this term goes away, and we're close to e to the negative x over 2. This is e to the negative x over 2. Okay. So one thing you'll notice about this function, the derivative here is actually 0. It's nice and flat there. So this is an even function. In other words, it looks the same if we flip it around the y-axis. Okay. It's an even function, and the domain is all real numbers. There's no problem plugging any numbers in here. The range, however, is just 1 and higher. You can't end up with a negative number, or actually any number below 1 coming out of the function cosh. Okay? All right. Any questions there? Now, if you ever had to plug numbers into these functions, like if somebody said, hey, what's sinh of 3? Almost invariably, what you should do, and I'll give you a rule for when you need to do this and when you shouldn't, is you should just switch to the definition. So the definition is of sinh is it's 1/2 e to the x minus e to the negative x. Okay, so if I plug in 3, that means I want 1/2 e cubed minus e to the negative 3. In other words, 1/2 e cubed minus 1 over e cubed. That's what this thing equals. Okay, or if somebody said, what's cosh of 0? Well, what you do is you just use the definition. You say it's 1/2 e to the 0 plus e to the negative 0. In other words, it's 1/2 e to the 0 is 1, e to the 0 is 1. That's just 2 over 2, which is 1. So whenever somebody asks you to plug numbers in or do other things with these functions, typically you're going to switch to the definition. Okay. The exception is that we have seen that the derivative of sinh, what we showed you earlier, is that the derivative of sinh, derivative of this function, turns out to be this function here. So the derivative of sinh is cosh, and the derivative of cosh is sinh. That's how these were cooked up, right? So if somebody asks you a derivative involving sinh and cosh, just leave them as sinh and cosh, because the derivative of sinh is cosh, and the derivative of cosh is sinh. Same thing for integrals. The integral, because the derivative of sinh is cosh, the integral of cosh is sinh. And you do not have to worry about any negatives showing up in the front, but you do have to worry about that plus c. Don't forget it. Same for the integral of sinh. Because the derivative of cosh is sinh, the integral of sinh is cosh. And again, don't worry about a negative sign. Okay? Okay, now from these, we can define other functions, just like we did with our trig functions. We could define, for instance, so we've got a definition for sinh. So e to the x minus e to the minus x over 2. And cosh is 1/2 e to the x plus e to the negative x over 2. I could define tangent, hyperbolic tangent, which maybe you could call tang, hyperbolic tangent, as hyperbolic sine over hyperbolic cosine. So if you did some, plugged in and did a little bit of simplifying, that would be e to the x minus e to the negative x over e to the x plus e to the negative x. I could define hyperbolic cotangent, so coth, which would be cosh over sinh. And we could define hyperbolic secant as 1 over, is secant 1 over sine or 1 over cosine? Secant's 1 over cosine, so this would be 1 over cosh. And hyperbolic cosecant, don't even ask me how to pronounce that, would be 1 over sinh. Okay? Now what I simply want to point out here is if you look at, take a look at page 397. So if you don't have your books out and open, go ahead and do that. So open your books to page 397. And I want you to take a look at the hyperbolic identities there. Hyperbolic identities. What you should see in that box are identities that remind you a lot of the trig identities that you've seen before. And this is one of the motivations behind us calling these trig functions. They obey identities that are very similar to the identities that you end up seeing among the trig functions. Okay, so for instance, on that, so this is the chart. This is the chart that I'm talking about right here. On that chart, you'll see something like, for instance, sinh of x plus y is sinh of x cosh of y plus cosh of x sinh of y. That sounds like a tongue twister, actually. That should remind you there actually is a formula that says the sine of x plus y is the sine of x cosine y plus cosine of x sine of y. That's actually true. Okay, you get a really similar formula for sinh and cosh. Okay, same for sinh of x minus y. All 4 of those equations are actually really similar. The left equations are a little bit different because we're dealing with hyperbolas instead of with circles. Okay. Yeah, so you'll see there's glimpses or reminders or these identities are very similar. So that's the motivation behind why we call these trig functions. So they're hyperbolic because they're based on that cosh squared minus sinh squared is 1 instead of cosine squared plus sine squared is 1. They're hyperbolic, and they're trig functions because they obey similar identities to the trig functions that we're actually familiar with cosine and sine. Okay. Now you might ask, why in the world are we talking about these functions? Do these even show up anywhere? And they actually do. And the simplest example, I won't get into a lot of examples of where these show up, but the simplest example of a hyperbolic trig function you actually see every day when you're looking at telephone poles and telephone wires. Okay? So it turns out that when you hang a wire from one thing to another, it does not go straight across, right? If I string a wire from one end to another, it doesn't go straight across. Telephone wires go like this, right? From one telephone pole to another. And it turns out this thing right here is not a parabola. It's actually a hyperbolic cosine function. So remember, hyperbolic cosine, so cosh of x, actually looked like this, right? This thing, if I were to plot, let me grab a different color. If I were to plot an axis right here, this equation is actually a hyperbolic cosine function. Now it depends on the height right here at the lowest point. But the equation here turns out to be a cosh of x over a. So you just learned the equation of a telephone wire, how this actually works here. So, so obviously, anytime you have anything that hangs, a chain, wire, other stuff like that, all of that is determined by hyperbolic trig functions. This is actually called, when you string two things from 2 points here, this is actually called a catenary. Let me write that just a little bit bigger so you can see that. Okay. Catenary. Right, so a catenary is actually determined by a hyperbolic trig function, hyperbolic cosine. Hyperbolic sines and cosines also show up a lot when you're dealing with differential equations. So this is the tie-in to sections 5.6 and 5.7. We're not going to get into those. But if you take further courses that start talking more about differential equations, these functions, hyperbolic sine and hyperbolic cosine, will end up coming up a fair amount. Okay, so you'll see them show up more. They're easy to differentiate and they're easy to integrate, so they're nice functions in that regard. They're just not functions that you're used to using right now. Okay, so we are not going to get into inverse hyperbolic trig functions. We're not going to get even into the derivatives of like hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant. Let me here just summarize what are the things that I want you to be able to do with these. What are the takeaways here, okay? So the thing that I want you to know about hyperbolic trig functions, I want you to know how hyperbolic sine is defined. Okay, so you need to know the definitions of these. So you should know their definitions. And you should know, just have a picture in your head of their graphs. Okay? You should definitely know what they look like. You should know that you should at least know the identity that cosh squared minus sinh squared is 1. Okay, that's an important identity to know. We're going to see it show up a little bit later. You should also know the derivatives, that the derivative of sinh is cosh, and the derivative of cosh is sinh. Now, if you forget and you remember the definitions, you can derive this, but you usually don't want to forget that. Okay? They're really easy derivatives. And you should also know the integrals. Okay? Again, these are pretty easy. The integral of sinh is cosh plus c. And the integral of cosh dx is sinh plus c. Okay? I am not going to have you work with hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant, nor their inverses. I'm not expecting you to know or work with any of those. Okay? And generally, unless you're dealing with the derivatives or integrals, so most of the homework, I think all of the homework problems from this section deal with, except for one of them, deal with the derivatives or the integrals of these functions, okay? Then you just use these identities, the fact that they're derivatives of each other, they're integrals of each other. But if I ask you any other question, you always go back any other questions besides derivatives and integrals, you typically go back to the definition and you use that instead. Okay, so anytime outside of derivatives and integrals that somebody's talking about sinh and cosh, usually convert them back into their e to the x and e to the minus x forms. Okay, that should give you what you need for hyperbolic trig functions. They won't come up immediately, but they may come up a little bit later, and when they come up, I don't want them to be a surprise. So, all right, so that should do it for 5.10 here. It's a little bit shorter lecture time, so you guys can take a break and then go to work on some homework problems from 5.10. I'm going to have Ms. Barabo pass out the homework sheet for the week after you get back. Remember, next week is spring break. The week after you get back from spring break, there's homework due on 5.10, which is today's lecture. And then tomorrow's lecture is on 7.1. Tomorrow's lecture will also be short, so you should have some time today to work on 5.10 problems, and then tomorrow you should have some time in class also to work on some problems. And you may have some questions on some of the homework that's due today, so Ms. Barabo may be able to answer some of those questions. And otherwise, I'll see you tomorrow. Have a great day.